But before we begin, I have a few housekeeping items to quickly review. First off, the audio for this webcast is through internet only, so I do recommend using a headset, earbuds, or listening to this presentation through your laptop or mobile speakers. Secondly, this is a one-way communication channel. You can hear us, but we cannot hear you. So if you do have any questions or comments, please use the chat feature to your right. And now I will hand it over to Justin to introduce today's presenter.
Thank you, Allie. So I'm Justin Billing. I am a managing editor here at Aspen Publishing, covering topics in the upper level doctrinal elective area. And I've had a great time working with our presenter today, Shahar Dillbary, on his new casebook, Law and Economics, Theory, Cases, and Other Materials. Shahar is a professor of law at Alabama Law, and he's got a pretty cool presentation for you all today. So I'm going to step aside and turn it over.
Thank you so much, everyone, and thank you for the very nice presentation. I will try to live up to it. So we're going to speak today about games and theory. And game theory and economics, generally speaking, can be very deterring to people. People think about economics and math and how do we do that. So I'm going to try to convince you, and that's what we did in the book, that games can be fun. I think we know that. But the theory can be also a lot of fun and not that complex. Now, if you don't have any background in law or in economics or in math, this is the right place for you. So what are we going to do today? We're going to start with an introduction to game theory, what it is, and then we're going to speak about two types of problems, two types of games. Static games, sometimes called simultaneous games, and dynamic games, sequential games. And when we're going to do that, we're going to speak about different types of strategies, what is an equilibrium, explaining that concept, and how do we get to an equilibrium. Big words, we're going to break them down. At the end, we're going to have time for Q&A session, but if there are any clarification questions, feel free to mention that in the chat room, and Alison will stop me, and I'll be more than happy to address them. Okay, what is game theory? Game theory is the study of strategic behaviors. These are situations where your decision depends on others' decision. So when you decide someone to do something, if I want to buy something, I'm going to enjoy certain consumption value. But sometimes what I do depends on others. Example is a chicken game. So in a chicken game, two people are driving, they're on a collision course, and each one have a choice to make. Keep driving or swerve. Now, I'm going to win if I drive and the other party swerves, but if the other party decides to drive and I believe that party, I will be the one swerving. So again, my decision depends on what I believe the other party is going to do. Another example is chess. I'm going to make my first move. I know that the other party is going to respond. They have another set of options. Knowing that after observing my choice, they're going to make their choice, and knowing what choices are available to them, ex ante, I think twice what I should be doing. Okay, so what do we have in game theory? Usually we have two or more actors, and then each player must choose a strategy, must make a move. In a plea bargain, the party must decide, whether to confess, take the deal, or keep silent. So think about two defendants, maybe they're co-conspirators, and each one is getting the deal. Each one has the same choice to make. Take the deal or keep silent. Think about factories producing. A factory may decide to expand capacity by a large amount, expand production by a small amount, maybe not expand at all, or maybe reduce or cease production. Now, the objective of each player is the same. It's simply to do the best you can. And finally, we have two types of games that we're going to speak about today, and there are differences in timing, but not exactly. We're going to see one of them is a static game, and the other one is a dynamic, the sequential game. So jumping in, what is a static game? A static game is a situation where one party must choose her options, what to do, make her move, without knowing what the other party is doing. One example, one situation when it happened, it's when you have to decide so simultaneously. In a chicken game, when I'm driving, I don't know what the other party who is driving is going to do. So I have to decide to keep go or swerve, not knowing what the other party is doing. But it doesn't have to be a simultaneous decision. Think about the plea bargain. We have two parties who got the same deal. Maybe they are co-conspirators, and they have a week to decide on it and sit on it. One man decides what to do on Monday, The other will decide whether to take the deal or not on Tuesday. But because each one doesn't know what the other party is doing, it's a static game. So speaking about plea bargains, this is a very interesting case, Page versus United States from 1989. And what's interesting about this case, there are many things that are interesting, but one of them is that game theory saved the lawyer in the case, not just the client. So what happened in that case? We have two parties, Page and Maurice, and they're both charged with armed robbery. Now, once caught, each one was offered a deal, a plea bargain. Both took it, both caved in. And what happened is, of course, that they met in jail. Once they met in jail, they figure out, well, we might have taken the wrong deal. Instead of taking the deal, we should have kept silent and would have spent less time in prison. How do you get out of the deal? Well, you throw your lawyer under the bus. That's one way to do that. So Page is filing a motion saying, well, the deal should be abolished. I should have my second chance because my lawyer, the counsel, rendered ineffective assistance. Basically, my lawyer committed malpractice when she suggested that I take the deal. So the question before the court is, what did the lawyer do? Was that the right decision to instruct the client to take the deal? The court denies the motion. Relying on game theory, the court says that the lawyer did the right thing. So how does that work? So this is the typical plea bargain. So what's going on over here? Imagine Page and Maurice, they're in different rooms right now, different cells, and each one, the prosecutor is coming to each one and offers the same deal. Here's the deal. He sends it to each one in their separate rooms. If you both confess, well, I have to throw you into prison, you cannot go out, and you'll get a 5-year sentence. If you both keep silent, I won't be able to put you behind bars for a very long time, but with the circumstantial evidence I have, with a lower offense, you're going to spend 2 years in jail each. However, if one of you confesses when the other one doesn't, I'm going to give you a sweet deal. You're going to get 1 year in prison, and with the help of your testimony, the other person is going to spend 7 years in jail. Your client is asking you, what should you do? And before going, I will just say game theory and economics, generally speaking, is a very important tool for lawyers today to figure out their duties and what's best for their client. So again, going back to the question, Page is asking you, what should you do? What should I do? Should I take the deal? The first thing you do to solve the problem over here, or to figure it out, is not to try to solve it. It's basically to rewrite the problem in a table form. And the table is going to do a couple of things. First, it's going to provide the parties. Here there are two players, Page and Maurice. It's going to chart the strategies they have. Maurice can either confess or Maurice can keep silent. And Page can confess and Page can keep silent. And now we just have to fill the payoffs. So let's start. If Maurice is confessing and Page is confessing, we are here on the top left cell, and I'm going to use Page payoff are going to be on the left-hand side by convention, and I'm going to use the same color so it will be easy for you. So if Maurice is confessing and Page is confessing, we know from here, each one should get 5 years in jail. That's the deal. If they are both silent, well, Page is going to get, this is Maurice is silent and Page is silent. So Page is going to get 2 years in prison, and also Maurice is going to spend 2 years in prison. If Maurice is confessing, this is the first column, and Page is silent, well, Page is going to spend 7 years behind bars, but Maurice is going to get the sweet deal and spend only 1 year in prison. And finally, if Page is confessing and Maurice is silent, we're on this cell over here, we know that Maurice is going to get the sweet deal of 1 year in prison, and Page will get the 1 year in prison because they confessed, and Maurice, who was silent, is going to spend 7 years. So far, I have not done anything. All I did is taking the deal and charting the strategies, the players, and the payoffs in a table form. This table is called the normal form of presentation. You really don't need to know that. It's simply a table. What do we do next? We have to discuss the assumptions that we have. We don't have too many assumptions, and they're quite simple in this case. One assumption is that not only do you know the deal that was offered to you, you also know the deal that was offered to the other party. And that is the case in a plea bargain. We tell you, the prosecutor was saying to each party, I've offered the same deal to both of you. So you know, if you are Paige, you know that Maurice can also confess or be silent, and you also know what's the implication of that. The second assumption that we have is that both parties are rational. And people go crazy about the rationality assumption. Here it means something very simple. You're going to try to do the best you can for yourself. And the best in this context is quite simple. Every party wants to spend the least time in prison. So each party is going to try to minimize the amount of time they may spend in prison. Okay, now that we charted everything, going back to our question, Paige, your client is asking you, what should you do? And now we're going to play a mental exercise. We're going to say something like that. Let's see if Maurice is confessing this column, what should Paige do? And if Maurice is silent, what should Paige do? And maybe we'll be smarter then. Well, let's start. If Maurice is confessing, when we're on this column over here, Paige has two options. Either Paige is going to confess and spend 5 years in prison, or Paige is going to be silent and spend 7 years in prison. Between spending 7 years and spending 5 years, it's definitely better to spend less time in jail, 5 years. And that error, I call it a preference error. It just says that basically between 7 and 5, Paige wants to confess. So bottom line, if Maurice is confessing, Paige is better off confessing. But hold on. What should my client do if Maurice is silent? Because Maurice may keep silent. Well, if Maurice is silent, we are here on the second column. And let's see what happened. If Maurice is silent, what's Paige's best strategy, best response? Well, if Paige confesses, he's going to spend 1 year in prison. And if Paige is silent, he's going to spend 2 years in prison. Between 2 years and 1 year, 2 years in prison is better, 1 year is better than 2. So look what happened over here. We have what we call a dominant strategy. No matter what Maurice does, Paige is better off confessing. If Maurice confesses, Paige is better off confessing. And if Maurice is going to keep silent, Paige is better off confessing. A dominant strategy, in other words, is a strategy that outperforms any other strategy. Here, confessing for Paige is always better compared to being silent. Okay, we gave our advice to Paige, but what should Maurice do? Maurice is playing the same exercise. Maurice is saying, hold on, Paige has two options, confess or keep silent. Let's see, what should I do? If Paige is confessing, we're on this row over here, Maurice can confess and spend 5 years in prison, or Maurice can keep silent and spend 7 years in prison. Between 7 and 5, well, 5 years is better. But hold on, what if Paige is silent? We're on this row. Well, if Paige is silent, Maurice has two options. Maurice can confess and spend 1 year in prison, or Maurice can keep silent and spend 2 years in prison. Between 2 years and 1 year, well, 1 year is present. It's better. So, once again, Maurice also has a dominant strategy. No matter what Paige does, whether Paige is confessing or Paige is going to keep silent, Maurice is better off confessing. And now we can solve the game. One simple way to solve the game is for each party to follow the dominant strategy. Because by definition, it is, we said, the best strategy for them. It outperforms any other strategy. So we know that Paige for sure should confess. It's better than anything else. Maurice for sure is going to confess. That's better for him than anything else. And as a result, what's going to happen is that both are going to confess. That is the solution of this problem, and that is exactly what happened in the case itself. Now, here's another way to solve it. It's a little bit more technical, but it's very, very simple, and newcomers to game theory and students of game theory absolutely love it. Here's the system. We already drew before those preferences errors. To find the solution, you just simply have to follow the arrows. So let's start. If I'm starting in this cell, I can go up with the arrow and take a left, and I'm getting here to the upper left cell. I cannot go back and I cannot go down. If I start over here, I cannot go to the right. I can go only up, and I'm here in the middle again. If I start here, I cannot go down. I can only go to the left. So the only solution is for both of them to confess. That is the arrow method. So we found two ways to find solutions. One way to find a solution is for each party to follow its dominant strategy. And the other way is to simply follow the yellow brick stones, in this case, basically the preference arrows. Okay, back to the case. Was the advice that the lawyer gave Page a sound advice? And the court says, well, if you know game theory, you understand that confessing is the dominant strategy. It's the best response. It's the best thing Page could have done. It's the inescapable result. Now, don't get me wrong. You can see from the table immediately that it's better for the party for Maurice and Page to be silent. If both of them are silent, each one will spend only 2 years in jail. And indeed, if they could have met each other and shake hands and struck a deal, maybe they would have agreed on 2 years. That's exactly what happened when they met in prison. But remember the game. In this game, in reality, each party is in a different cell. They are not allowed to coordinate with each other. By definition, a static game is a game when you have to make your decision without being able to observe the other party's decision. And that's what drove them to this result of confessing. That's why prosecutors designed their plea bargain the way they designed it to result in this inescapable result that both of them are confessed. This result was by design. Okay, so far we spoke about a situation in this case when there is only one solution. But I'll already immediately tell you that sometimes there are multiple solutions, what we call multiple equilibria. Equilibrium is a fancy word. We'll explain in a second what it means. So sometimes there is one solution, one equilibrium. Sometimes there are multiple solutions, multiple equilibria. And sometimes there may be no solution. Let's discuss a case when there are multiple equilibria. We'll start first with a fun game, a chicken game, and then I will explain to you and provide you one application of that chicken game in a case. There are many applications for those games. So what is a chicken game? Well, a chicken game is a very simple game. You have two drivers, A and B in my situation, and they have only two strategies. A driver can drive and stay on a collision course or swerve. Now, unlike time in prison, what are the parties trying to do over here? It's not about money. It's not about time in prison. It's about preferences. So let's try to figure out what's the best case, second best, third best, and worst case scenario. And focus, please, on the middle ranking over here. This is if you want the preference ladder. So if you are driving, your best case scenario, if you drive and the other party swerves, in which case you win. So I gave it the largest number, 3. That number doesn't mean much. It's not money. It's not utils, if you learn philosophy and utilities. It just means this is my number one priority. This is my best situation, my best case scenario. The second best scenario is if you both swerve. Then there is a tie, there is no winner. So it's not as great, but it's not as bad compared to other options. If I swerve when the other one keeps driving, I lose. So that is definitely inferior to a tie or winning. And really the worst case scenario is if I drive and the other party drives and we both collide. That is really not good. So those numbers, again, what are they? They're just a preference ranking. They have no meaning beyond that. By the way, can you say that winning is 3 times better than when both swerve, when I swerve and the other party drives, because it's 3-1? The answer is no, you cannot say that. This only means that winning is better than losing. And to show you exactly what I mean that it has no meaning, look at these preferences over here on the right column. It's exactly the same order. Basically, winning is number 1, a tie is lower, 0. It means it's less good than 1. When I swerve when the other party drives, that's -1. That's worse than both swerving and worse than winning. And both of us driving and colliding, I gave it -2, which is worse than -1. Colliding is better than being in one piece, and colliding is worse than being in one piece and losing. So we're going to use those rankings to try to solve the chicken game. So if I'm driver A, what should I do? Remember, it's a static game. I have to make a decision, knowing you have the same options. I know your preferences as well. You want to win, you don't want to lose, and you don't want to collide. So what we need to do is, first of all, create a table. So here's our table. We have player A, we have player B, we have the strategies, drive or swerve, and we have the preferences we just discussed. To figure out what should A do, A plays the mental exercise. If B drives, what should I do? And if B swerves, what should I do? Well, if you're a driver A, you have to say, if B drives, what should A do? Between keep driving and colliding, that's -2, that's not good, or swerving and losing, well, swerving is better than driving and colliding. -1 is better than -2. Well, hold on, what if B swerves? Well, if B swerves, I can keep driving and I'll win. Or I can swerve and that will be a tie. 0 is worse than 1. 1 is better than 0. Winning is better than a tie. And look what happened now. We do not have a dominant strategy. This is not like the prisoner dilemma that we had before, where no matter what the other party did, you wanted to confess. Here it's different. For A, it's better to swerve if the other one keeps driving, but it's better to drive if the other one is going to swerve. Okay, so we know what A is thinking. What should B do? Well, B is going through the same exercise. B says to himself, if A drives, I can keep driving and collide, that's -2, or I can swerve, not great, it's -1, but guess what? -1 is better than -2. So I'm creating my preference arrow. But hold on, what if A swerves? Well, if A swerves, I can keep driving and win, that's 1, or I can swerve as well, that would be a tie. Well, I definitely want to win, 1 is better than 0. So now we can solve the problem. We don't have a dominant strategy, so that was one way to find a solution, which we cannot use right now, but we can use the arrow system. Let's go with the arrows. Look at that. If I start over here, I can go to the right, I cannot go back, and I cannot go down. That would be one solution. If I'm starting here again and I go down, I can go up, I can go to the right. That's another solution. If I start here, I can go to the left and I'm stuck here, or I can go up and I'm stuck here. We have multiple equilibria. We have 2 solutions. What does that mean that we have 2 solutions? A common mistake that people are doing is saying, well, you have 2 solutions, so one of those 2 options are going to happen. And that is wrong. When you have multiple equilibria, game theory is it's a humble area. Game theory says, I'm sorry, I cannot predict what the parties will do. It could be that they will both drive and collide. It could be that they will both swerve and there will be a tie. And it could be that one will drive and the other swerve. We just don't know what the parties are going to do. Okay, let's assume now that one of them, A, is a really devout driver. A preferences is to drive no matter what. A prefers to collide rather than lose. A will always prefer to drive rather than swerve. Will there be a different solution to the game? The answer is possibly. Look at that. Basically, what we are saying is that A has a dominant strategy to drive. No matter whether B is driving or B is swerving, A is going to drive. That's A's preferences. What would B do? That's the question. Well, here's the problem. In a chicken game, that's the name of the game. You play who's going to be the chicken. So I'm going to say, I will never swerve. And you are going to say, I will never swerve, because we are trying to convince each other that I'm always going to drive, so you will swerve. So If B doesn't believe A, they might collide or might not. But if B believes A, B would swerve. There is no B doesn't have the same preferences. We said that for B, you want to win if you can. And I too.
Hey, Professor. Doing a quick interjection that we cannot see your cursor. I think we lost it real quick.
Here we go. I appreciate that. Can you see it now?
No worries. We got it back. Thank you, everybody, for pointing that out.
I appreciate that. Thank you for saying that. So, if B believes that A will drive no matter what, remember for B, winning is great. Tie is not as great, but fine. The worst case scenario is colliding. So if B, where's my cursor? Here we go. If B believes A, B would swerve, or even better, if I know I'm going to lose, I'm not going to enter the game to begin with. Why have the humiliation? So now the question becomes whether A can convince B that A is going to drive no matter what, because that is cheap talk. I'm going to say I'm going to drive, and you say that. That's the name of the chicken game. So A needs a commitment device or a credible signal that this is not cheap talk. How do you do that? Here are a couple of possibilities. One is that A can post a bond. What does that mean? I can give $1 million to Allison, and I will tell Allison, you know what? If I swear, you take it and you do whatever you want to do with that. Now you might believe me more. It can be even a more credible signal. How about in the beginning of the game, I'm going to disable my brakes in front of everyone, disable my steering wheel. Now everyone knows that if I'm driving, there is no way I can brake or I can swerve. So that's a credible signal. And in such a case, the game will change. Because right now, what will happen is that we know A is only going to drive, and in such a case, B is either going to swerve or avoid the game. A is going to swerve, here we go, or avoid the game altogether. Okay, so now we're going to say the chicken game. Yay. What does that have to do with the law? Actually, a lot. I'll give you one example. We spoke about criminal law. Let's try to speak about bankruptcy. So this is the case, the Boulder case, and it's from 2005. And the facts are quite simple. This is a Chapter 13. No worries if you don't know bankruptcy. We have a debtor and lots of creditors. And the debtor's lawyer is asking for more money because there were a lot of work that the lawyer had to do. Now, the lawyer for the debtor is filing a motion, please give me more money. And of course, if the lawyer is getting more money from the limited pie, that means less money left for the creditors, and therefore less money left for the lawyers of the creditors. But what happened, even though the lawyer is filing this motion, saying, I want more money from the pie, no one objected. No creditor objected. The question before the court was, should I infer that if no creditor objected, therefore they all agree, and I should allow the lawyer to get this additional amount? And basically, based on game theory, the court says, no, I am not going to infer that they agreed. Here's why. Before I go to the why, I want to switch slides very quickly to show you something. This is the chicken game we just spoke a second ago, and I want you to focus on the table. And you will see I'm going to switch to the next slide, and it will be the same preferences, the same parties, A and B, just the strategies will change from drive swerve to something else. Look at that. The same table, just the strategy change to do not file or file. So what are the options here for each of the parties? If you are a creditor, you have two options. Either you file a motion saying, or respond saying, no, I do not want you, the court, to allow more money for the lawyer because that's bad for my client. Or you can sit still and not file anything. These are the two options you have. You have no more options. So let's try to rank. If you are a creditor and you are the creditor's lawyer, what's best for your client? The first best, if you do nothing, and someone else files an answer saying we object, this way, you free ride. Someone else is spending the money on the answer to the motion, and your client benefit because there will be an objection. So I gave it the number 3. Now, another possibility, if you file and all the many other creditors, they also file, well, you're going to lose some money because you will have to spend some money on writing the answer, but there is no free riding. Now, it could also be the case that you are going to file the motion and no one else will, and in which case you again lose some money for writing the answer, but now people are free riding on you. So maybe you're less happy about that. And the other option, the worst case option, this is colliding basically. No one files the motion. The court allows basically the lawyer of the debtor to get more money, and every creditor is going to get less money. This is the worst case scenario. And if you play that game, this is exactly the chicken game, you get to the same result. You get multiple equilibria, 2 equilibria. And again, we know now that when you have multiple equilibria, everything may happen. It could be that no one will file the motion. Guess what? That was one smart court. This is what the court says. The court is recognizing, literally using game theory in the case. And the case is available in our book. You see the expert, and we analyze that. The court says, unless the rules of this game, this is the wording of the court, unless the rules of the game are altered, well, creditors may do nothing. They may end up in this cell over here. No one files the motion, which is the worst case scenario, because that means they all object, but they do nothing about it, hoping to free ride on another, and the result is that the court may allow the motion. The court says, no, I'm not going to allow it. I understand the dynamic the court is saying, and we have to alter the rules of the game. And the court is giving 2 possible solutions. One solution is me, the court. I am going to review. Even though no one objected, I'm not going to infer that the creditors agree, because I understand the dynamic that they don't agree, but they also want to save on resources. So I will just do their job. I will review it and will decide if the request for more resources, for more money, is reasonable or not. The other option that the court is giving, interesting enough, which is also a good option, which the court tried in the past and it failed, by the way, is to reduce the cost of cooperation. Remember Paige and Maurice, they met in jail and they coordinated? Well, the court said, let's do that. The court said that we can ask the trustee to get all the creditors together in one room, and then they can decide whether to file a motion, and maybe each one is going to chip in some money for the party who is going to write the motion. That did not work. Cooperation costs can be very high for many reasons, but the court did review the motion. So this is your chicken game in real life, and what's nice over here, you can see it's exactly the chicken game. That table that we have did not change. The only thing I changed was the strategies of the parties. Okay, so far we have static games, a situation where you must make a decision without knowing what the other party is doing. We saw that you can solve it in 2 ways. One way is follow dominant strategies. When you don't have a dominant strategy, you can follow the error system. Here are the preferences errors. And we saw a case when you have one solution, and we saw a case that you have 2 solutions. Solutions are just another name for a very fancy term, Nash Equilibrium. So what is this mystical term, Nash Equilibrium? In Nash Equilibrium, in equilibrium, each party chooses a strategy which is the best response to the other person's strategy. So it's a stable point. Think about Paige and Maurice. The strategy each one chose is to confess, which was the best response to the other party's actions. We saw, what should I do if Maurice is confessing? Well, the best response was to confess. What should I do if Maurice is keeping silent? Well, the best response was still to confess. That was a Nash equilibrium, because it was stable for both parties to confess. Okay, I want to show you now I should start by saying that the dominant strategies and eliminating strategies, I'll explain maybe later what that means, it doesn't always work. You saw that. Sometimes you don't have a dominant strategy. So one way to solve the problem was to use the arrow system. But I want to give you a better tool. It's called the best response. So here's another static game. Consider two firms that are already in the market. And let's say after 10 years in the market, they're in period 10. In period 10, they have to decide, what am I going to do next year? Well, each one here, we have two parties, A and B, but they have three strategies. So you can see you can have more than two strategies. Look at firm A. Firm A can decide not to expand its production, or it can decide to expand its production by a small amount, or it can decide to expand its production by a large amount. And party B doesn't have to be, but in my case, they also have the same options. They cannot expand by a small amount, or expand by a large amount. So we have the parties, A and B. We know their strategies. And here I already gave you the payoffs from each situation. Why are those numbers? I can explain. By the way, this is an example, again, that we have in the book. We analyzed that. It's taken from an equal book on game theory. This is not an example that we manufactured. But it makes a lot of sense. Why is that? You can see here, if both expand large, very competitive market with a lot of products in the market, well, they're not going to make a lot of money. Each one is going to make zero. If neither is expanding, it's more like a monopoly or a very tight duopoly, so they're making a lot of money. But we don't need to get into that. These are the payoffs. So what do we do with that? Okay. What we do with that, how do we find the solution here? Well, we're going to use the best response method. This is a fun, easy method. What do you need to do? You have to figure out what's each party's strategy, and then figure out what's your best response to that strategy. So let's see how it works. It sounds complicated, but it's very easy. Assume I'm A. I'm B. I'm looking what happened. A can do a number of things, not expand, expand small or large. Let's assume A is going to expand to not expand at all. No expansion. We're in this row. What should I B do? What should be my response to A not expanding? Well, look at that. I cannot expand. That can be my response, and I will make 18. Or I can expand small, and I will make 20. Or my response can be expanding large, and I will make 18. Between 18, 20, and 18, well, I make more here. So if A is not going to expand, B's best response is to expand by a small amount. But hold on. A may decide to expand by a small amount. We're here on the second row. So if A decided to expand by a small amount, what should B do? Well, if B is going to respond by no expansion, B is going to make 15. If B's response is going to expand in a small amount, B is going to make 16. And if B is going to respond to A by expanding large, B is going to make 12. Between 12, 16, and 15, 16 is the best. So when A is expanding by a small amount, B's best response is also expanding by a small amount. Finally, if A is going to choose to expand by a large amount, what is B's best response? Well, B cannot expand and make 9, expand by a small amount and make 8, or respond by expanding large and make 0. Between 0, 8, and 9, the best option for B is to expand, to not expand at all. So now we mapped B's responses to A's strategies. Let's switch. If I'm A, how should I respond to B? Well, I know that B may decide not to expand. How should I A respond to that? Well, I can either not expand and make 18, expand by a small amount and make 20, or expand by a large amount and make a twin. Between 18, 20, and 18, 20 is better. So if B is not expanding, A's best response is to go small. But hold on. What if B is going to decide to expand by a small amount? What should A's response be? Well, A cannot expand and make 15. It can expand small and make 16, or expand large, go large, and make 12. Between 15, 16, and 12, A's best response is to go for a small expansion. And finally, B can go large. What should A do if B goes large? What should be A's response? Well, A can decide not to expand and make 9. It can respond by a small expansion and make 8. Or A can respond by a large expansion and get 0. Between 9, 8, and 0, 9 is the best option. Now that we mapped everything, we have a solution. A cell, which is a combination of strategy. This cell over here in the middle is when B goes small and A goes small. This cell is both parties' best response. And therefore, that is the equilibrium. So this is the best response method. Now, so far we spoke about static games. In this case, each firm was on the market already. Each firm had to decide, what am I going to do next year? And that was a private decision that the other party was not privy to. So each party had to decide on its strategy, one of the 3 strategies, without knowing what the other party is going to do. That's a static game. Let's change the nature of the game. Let's think about those 2 firms, A and B. But now it's a sequential story. Now A is going to decide first what to do. B is then going to, and A is going to announce its decision to the world. Next year, I'm going to raise prices. Next year, I'm going to build a new factory. After A makes that announcement, B is observing it, and B is making its decision. So this is more like a chess. You make a move, I observe that, then I make a move. So will the result be different if we change the nature of the game from a static game to a dynamic game? And the answer is yes. Actually, the result may change. How do we solve dynamic games, sequential games? We don't use the table. We're actually going to create a tree diagram that maps those sequential steps. We call it the extensive form representation. You do not need to know that. This is just a term of art. If you open an Econ book, that's the term you will use. I'm just going to call it a tree. So let's chart the tree. Here's firm A. Firm A has 3 options, 3 strategies. It can either go large, small, or NE for no expansion. Once firm A made the decision, let's say to go large, well, firm B, that's the node, it has also 3 possible moves. I'm charting them. Firm B can then decide to go large, small, or no expansion as well. So now we have a tree. The nodes, again, provide the parties. The actions are basically on the moves. And now we have to fill the payoffs. So here's the complete tree. If firm A goes large, firm B can respond by going large, small, or no expansion. If firm A goes small, firm B can respond by going large, small, or no expansion. And if firm A decides not to expand, firm B can go large, small, no expansion. Now we have to fill the payoffs. So what are the payoffs? Well, we can use the table to fill the payoffs. Look at that. If firm A goes large and firm B then respond by going large, it's this cell over here, right? Large, firm B goes large, and firm A goes large. And in that case, A gets 0 and B gets 0. What if firm A goes large and firm B goes small? What are the parties' payoff? Well, let's see. If firm A goes large, you can see that on the bottom row, and firm B goes small, that's the middle column, we know that A is going to get 12 and B is going to get 8. And finally, if firm A goes large, here we go, firm A goes large, and firm B respond by not expanding, where in this column over here, firm A goes large, firm B is not expanding, that's the first column, and therefore firm A is going to get 18 and B is going to get 19. And if you continue with the same process, you're basically going to get this. This is the entire tree with all the options and the payoffs. So let me just repeat what we have. Firm A must decide on a strategy today, go large, small, or not expand. Once it's making a decision, let's say it decided to not expand, firm B is then in period 2 making its own decision, going large, small, or no expansion. And in black, we have film B's payoff. And in maroon, we have films A payoff. How do we solve this problem? We're going to use a backward induction, or a less fancy name. We're just going to roll it backwards. What does that mean? Film A is going to play a mental exercise again. If I'm going to go large, what would happen? What would film B do? What will be film B's response? Well, we know that. Look at that. If film A is going to go large, what would film B do? Let's get into film B's shoes. Film B can go large and therefore make 0. Film B can go small and make 8. Or film B cannot expand and make 9. So we know that if film A is going to go large, film B will get between 0, 8, and 9, will decide to go 9. Okay. By the way, if film A goes large and film B decides to go no expansion, film B will make 9, but now we know that film A in such a case will make 18. Let's see, at 15, film B is going to respond by expanding on a small amount. So now film A knows that if it's going to go small, film B will go small, film B will make 16, and film A will make 16. And the final option, if film A decides to not to expand, how will film B respond to that? Film B can go large and make 18, go small and make 20, or not expand and make 18, which means film B would prefer to make the most, 20. Finally, now, film A can take a step back and figure out what should it do. Now, film A knows that if it goes large, film B will respond by no expansion, which means that A will get 18. And if film A decides to go small, film B will respond by going small, and film A will make 16. And if film A goes to no expansion, film B will decide to go small, which means that film A will make 15. So film A is thinking, what should I do? End up with 18, 16, or 15? Well, that's an easy choice. Film A is going to go large, which means film B will not expand, and film A will make 18. Look what happened over here. When we had a simultaneous game, you can see that in the table, we had an equilibrium of both of them going small, and A got 16. But when we changed the nature of the game where A goes first and B goes second, it's a new equilibrium where A gets 18 and B gets 9. There is an advantage here of moving first. This is an example of a first mover advantage. The first to move get a huge advantage, increasing profits from 16 to 18. Let's do something fun with that, just to cement what we've done about the backward induction, because sometimes it's hard to do. So here is the fun exercise I have with my kids. I have 3 kids, and they usually fight over donuts. But you can think about the parking lot. How do you divide it? How do you share a donut? It's the same problem. Now, if I'm going to give one of my kids to divide a donut, I'll tell you exactly what's going to happen. However she divides it, whether it's equal or not, even or not, the other person is going to cry, it's unfair, she got the bigger piece. So what's the solution? The solution is to give one kid the option to divide the donut and the other kid to choose what she's taking. Or if it's the neighbors, one neighbor decides on a division, the other neighbor is deciding which parcel to take. And let's see the game over here. The first player in my story is going to cut. It can be either uneven or even. These are the only 2 options. Now, if it's going to be an uneven distribution, a big piece and a small piece, player 2 is going to be the chooser. Player 2 will definitely choose the big piece because a bigger donut, usually, for the kids at least, it's better than a small donut. So that's what's going to happen. That's going to be the best case scenario for the second player. They got the bigger donut. They will not choose the small donut, the small size, the small piece, because that's the worst case scenario. If player 1 cuts it in even portions, player 2 will be indifferent. In any case, it's going to be half the piece. So they will choose, that is the second best option. So again, first best option, got the highest ranking, I'm getting the bigger piece. Second best option, I'm getting the middle-sized piece, 50%. And the worst case scenario is going to get the smaller piece. It's the same preference for player one. Player one, if player two gets a small piece, it means that player one gets the bigger piece. And that's why it's the highest ranking, 3. If player one cuts it even, player one knows whatever happens, it's going to get a side and a half, which is great. And the worst case scenario is that player one doesn't cut it even, for example, by mistake, because we're not perfect. Then player two is going to choose the big piece, and their player one will end up with a smaller piece. So bigger is better than 50%, which is better than less than 50%. How do we play the game? If I tell one kid, you divide, and I tell the other kid, you choose, what will happen? Let's play the game. Player one can say something like that. If I go even, what will my sibling, player two, do? Well, they will choose the big one. They will not choose the small one, 3 is better than 1. So this is what's going to happen. But hold on, what if I'm going to cut the donut evenly, in even pieces? Well, in such a case, my sibling is going to get 50%, and I'm going to get the other 50%. What should player one do? Well, player one knows that if it's going to be uneven, player one is going to choose big, and player two is going to choose big, and therefore player one is ending with the worst case scenario, a small piece. But if player one cuts it evenly, player two will choose one of the halves, and therefore player one will get the other half. So guess what? That's going to be the solution. This is another case of a sequential game. Let me stop over here. And what I want to do is say a couple of words on what we've done and just open it to Q&A. So we spoke about games and theory, and there's a lot of theory behind these games. And many of those games, we speak about games, chicken and whatnot, or Prisoner's Dilemma, they have real-life application, especially in the legal arena. And in the book, we first of all provide a theory in a way that everyone can understand. You don't need to know math. If you know first grade math, you're overqualified in terms of your math. And we try to explain it in a way that will be as intuitive as possible. We think it's quite intuitive. The other thing we did, we provide the application, and after every theory, there is a main case, like the Page and Maurice case, and then there are permutations, there are notes. And in each note, what we do, we provide examples, so you can exercise what you learned, but you also see different cases, and how in different cases, when you change the rules of the games, the result changes as well. So that's another way to go deeper with your understanding. Finally, for the professor in the audience, we have a very, very detailed teacher guide. So even if you don't game theory, you don't know game theory, or you don't know law and economics or economics, you can definitely pick up with that very detailed teacher guide, and you'll have basically everything you need, including slides and the type of diagrams that we just used. Again, this is the co-work with Bill Landis, who is a dear friend and for many years a mentor. And we're very proud of that, and I'm more than happy to answer any questions you guys may have.
Wonderful. Thank you so much for your presentation today. As mentioned, we are at the Q&A portion, so if you do have anything to ask, please use the chat feature and I will read it out loud. And looks like we have some to get started, so here we go. Can you think of any other examples that students may relate to? Any other fun examples?
Suddenly cannot see anything. Let me try to see why that is the case.
No worries.
So let's try this. Hello? Are we here? You are here, so where are you?
Yep, I hear you.
Cannot see. Okay. I'm sure I cannot see anything, but I can stop sharing. Okay, here we go. We made it. Sorry. What is the question again?
Here we go.
Yeah.
Can you think of any other examples
I don't know
that
if that's
students
fun.
may
There's something
relate to?
fun for
Any
me
other
and
fun
something that is
examples?
fun as in TV fun. So you can show many things with game theory. For example, the trilogy of the commons is one example of another game. Each party, we have a forest. We have two parties next to a forest. Each one can go and cut the entire forest and sell the lumber now, or they can wait. The forest will be bigger. The value of the forest will be better. And if they both cut it in the second period, guess what? They're both going to make more money. So each one has the option of cutting now or cutting later. And if you play the game, it's a version of the prisoner dilemma. What happened is both confess, both cut now, even though it's in their interest to collaborate, cooperate, and wait for the second period. That is fun for me. That is property law. But here's something much more fun than that. So for Bachelor Nation, those who like The Bachelor, we have The Bachelor, we have The Bachelorette, we have The Bachelor in Paradise. I think that's showing right now. We used to have The Bachelor Pad. I don't know how many of you remember that. In The Bachelor Pad, there were folks who were previous participants in The Bachelor and Bachelorette, and they had to team to couples. And they had to compete throughout the show. And at the last show, we have one couple standing. And then they face a dilemma. This is the show, and you can watch it on YouTube as well. And I showed that to my students, but it's a fun exercise of the prisoner dilemma. These are the rules of the game. They got $250,000. But here's the deal. They have to go behind something over there, like in a private room, and decide to share it or to keep it. If one decides to keep everything while the other decides to share, the one who decides to keep keeps everything. They get the $250,000. They get a check for $250K. If both of them decide to share, each one gets $125K, half the amount. If both of them agree and decide to keep, what happened is that neither of them is getting the money. The money goes basically to the other participant on the show who didn't make it to the final. And if you play the game, it's a prisoner dilemma. And there are a couple of versions. There are couples. There's one couple I think that were engaged before. They have an ongoing relationship. And we didn't speak about a repeat player game, but that is sort of that. And they decided to share. And there were couples that there was nothing over there between them. They really didn't click. There was nothing that they felt they should trust each other. And they, of course, decided both to keep, and the money was lost. So when I was watching those shows, based on their relationship and knowing game theory, it was easy to figure out what's going to happen. So again, you can do so many things with game theory. It can be just watching a TV and speaking about that with your student. They can definitely relate to that. Explaining property, torts, what have you. Game theory is a very useful area of economics and the law. I hope it's not too long. Go ahead.
Next question is the small expansion the best response for each party because it's the best in 2 out of 3 scenarios? And it does apply to
let me try to put the slides again. Let me try
the
to
scenario for
share
expansion.
it, and I will make an effort. Let's do this. Okay. And let me now go over here and do share. Oh, sorry, that's the wrong button. Let me do here and try to share. And let's do share. And let's see if it's sharing. It may take a second. Oh, here we go. So this was a dynamic game, but this is the simultaneous game. And we saw their best option, the equilibrium, was for each one to share. And can you repeat the question, Alison?
Yes, is the small expansion
the
the best
choice
response
given
for
the
each party because
So
it's the best choice in 2 out of 3 scenarios?
That's a great question. And not only is it a great question, it leads me to something else that I want to show you. Let me show you this. And I'll skip that. Don't freak out. Oops, I skipped too much. Let me go Open here. Oh, here we go. And I think you can see that now. Okay, so look at this over here, this situation. Let's focus on this cell, for example. Here, B is not expanding and A is not expanding. Is that an equilibrium? And the answer is not. If B is not expanding, A's best response is to move from 18 to here, to move small. So we can basically cross that. That is not a good best response. Let's look at the second cell over here. Let's say A is deciding to on a small expansion. Will B remain here with no expansion? And the answer is no. If A decide to extend small, B's best response is not to expand, not no expansion, but to move to small expansion. So we can also say that this cell is not going to work out. This is basically what we call the cell-by-cell analysis. And if you go through all of the cells, you will see that it will never be stable. Remember the definition of a Nash equilibrium? Each one chooses the best strategy, the best response, and no one has an incentive to deviate. And in every other cell that you will choose, one of the parties will have the incentive to deviate. I'll give you one more example. Let's choose randomly this cell over here. If A goes large, so we are here on this cell, and B is considering going small, is this a stable situation? No. If A goes large, B can respond by here, no expansion, and make 9. So this is an unstable cell. And if you go cell by cell, you get this basically. Each cell will be crossed somewhere. It will never be the best response for both parties. The only cell in this game for both parties that it's the best response, it's one cell. Now remember, there can be, if I change the numbers, there can be maybe no equilibrium, there is never a best response, and there can be multiple equilibria, multiple cells where you have those two cells that are best responses. Just in this specific game with this specific payoffs, numbers, preferences, there is only one cell which is the best response for both parties. Yeah.
Great. Thank you very much. All right. I do not see any more questions at the time. So I will pass it back over to you.
Just want to thank everyone for chiming in. We hope that you will try to check out our book. We invested a lot of thought in it. It's actually unique of its kind if you compare it to any other book, and that's why we use that. Bill has been teaching law and economics for over 40 years. I've been doing that for almost 2 decades. And what we were trying to find is something that will be intuitive. So people, and especially students, will not be deterred by the numbers, right? That's why we go sometimes to law school. 2, we try to find something that really marries law and economics. So the way our book is structured is, first of all, in every chapter, we provide the theory, like a textbook, not a casebook. So here's game theory. Here's what you need to know about the theory. Then we start with one leading case, an actual case that the theory you just learned, the economic theory, explains. Then we have many notes and permutation after that specific case. And in each note, we either provide exercises, so you can try to see if you understand the theory, and multiple cases where a case was either decided for the right reason, and economics explained that, but the court is not using the same reasoning, but economics explained why it was right. Or the case was decided in the wrong way. If you understand the economics, you understand this is the wrong decision. So you have a lot of the law and a lot of the economics. On top of that, we married both methodology chapters and subject matter chapters. So for example, if you want to learn about supply and demand, there is a chapter on supply and demand, and in that chapter you find criminal law, torts, contracts, every area of the law with supply and demand being the theme. And again, in that chapter you have the theory, then the cases, than the nodes. The same thing for decision under uncertainty. You have, that is the theme, and you have different areas of the law where uncertainty plays a role. It's basically every area of the law. Some chapters are designed according to the substantive theme. So we have a torts chapter, a property chapter, incompatible users chapter. Now in those chapters, you will have game theory and supply and demand because the theme is the substantive area and we use different methodologies. Another fun thing that we did, we made sure that each chapter is a standalone. So if you teach torts, for example, and you just want to use the law, you want to teach your students about, in 1 or 2 classes, about the law and economics of torts, you can just use the torts chapter. Even if you didn't do the decision under uncertainty or game theory or supply and demand, that chapter will give you everything you need, including the tutor guide. So it's modular, it's marrying textbook and a casebook. It really marries the law with the economics. It gives you the theory and application to the law. And we really hope you'll enjoy it. And of course, if anyone has any questions at any point, let us know. It's the first edition. If there are any errors that you think that you found, we are humans. That could be the case as well. We'd love it if you let us know what you liked in that book, what you didn't like, so the second edition can be even better. Thank you so much for considering us.
Thank you. Today's webinar has now ended. I want to thank everybody for attending, and I hope you have a great rest of your day. Thank you.